Okay, so today we will discuss about numerical derivatives. And so, needless to say that derivatives are very important in physics or in engineering. So we need to compute derivatives all the time, right? Okay, so derivatives is all over, right? I mean, finding velocity of a particle, finding acceleration, d psi by dx in quantum mechanics is everywhere. So let's see how we can do numerically. So numerically means we will be given data points which are discrete data points. So given x, we have y's, and we will not have everywhere but discrete data points. Okay, and let's see how to do it. So in physics, of course, Newton and Leibniz both, we should give credit to both. They give the formula. I mean, f prime x is fx plus s minus fx divided by h. Now, in physics, we take h going to 0, or in mathematics, in fact, h going to 0, right? I mean, h is going to 0. But in numerical computation, we don't have this this luxury. H is always finite. Okay, and so there always is an error. Okay, always I qualify for what I'm going to teach today. FD method, called finite difference methods. There's error, but we can also do things using a spectral method, which I will tell you later. With Fourier transforms, we can get exact derivatives. Okay, even with computers. Okay, but that is later. We'll do it later. Now, so in fact, we have all the machinery. We can just use that to solve. So to compute the derivatives, so we have f of x, which I approximate using a Legendre polynomial. Okay, so this is a Legendre polynomial. Not Legendre, Lagrange. No, apologies, Lagrange polynomial. So with 2 points, we have P2x. This 2 is the number of points. With 3 points, we have P3x and so on. Okay, and I'm approximating. So let's write f of x as a Lagrange polynomial, and it is that, right? I mean, we derived this. It's a linear function which passes through fi and fi plus 1. So I also would like to say that I already discretized data. So I have x0, x1, x n minus 1, and there's in fact the data points are here. So I'm looking at points at I plus 1 and I. So these are the 2 points, okay? I and I plus 1. Okay. You can of course take any 2 points. They're adjacent points. They're just adjacent points. So this is a Lagrange interpolating function for 2 points. Now we can compute derivative. This is straightforward. It's a linear function. So the derivative will be simply we can just look at it. We can just compute it. So this is linear. So it basically is 1 in the numerator, and so bottom will be what? Xi minus xi plus 1. So now I use a notation xi plus 1 minus xi equal to hi. Okay, that's my notation. Okay. So what is this guy? Is negative of the hi. Right? Hi is a step. So minus hi fi. This one derivative will be xi plus 1 minus xi in the denominator. So is 1 by hi fi plus 1. Okay, so that's what I've written it here. So this is a derivative. Okay, now right now I also make a new definition that how are you computing the derivatives? Okay, at present there is only one derivative. First derivative is only a single number, and but we make a contrast. Say, well, if I have 2 points, right now of course with 2 points my derivative is just the slope, right? The derivative is the slope. But we say that if I take the derivative at xi looking towards xi plus 1. Okay, I look ahead like in a in a trekking in a mountain. If I at a given point, you just look at this mountain up, so you'll get a slope, and that slope is called forward difference. Okay, this is a name, forward difference. Now you can also get the slope by looking downward from the upper part of the mountain and look down. Okay, of course the derivative definition is exactly the same, which is um, fx plus h minus fx divided by h. Okay, so it's not that when you look down then slope is negative. Still the slope is positive, but you are looking downward from top. So that is called backward difference. So this is computed at xi plus 1, backward difference, and forward difference is computed at xi. For 2 points, they are exactly the same, but with more points, they will not be the same. Okay, I will just state the formulas in the next slide. Okay, is that clear? So this definition you should remember. Forward difference is looking ahead. So I have 2 points xi and xi plus 1. So I compute the derivative at xi, then I look up forward. But if I compute the derivative at the ahead point looking backward, so xi plus 1 looking backward, then I have called backward difference. Okay, so these are the two different derivatives. We'll have some more. Just give me a few more minutes. I will tell you that much. So 2 points, just straightforward. Formula is just fi plus 1 minus fi by hi. Now we can show it graphically as well. So I have 2 points xi and xi plus 1, and the real function is this black curve. Of course, I approximate that function by P2, which is this dashed line. Okay, actual slope, of course, is the red line. Okay, but I can't get actual slope because I don't have the black curve. I really have no information. I only have information at these 2 points. So I basically get the slope. This one is approximate slope, and that is numerical derivative. And this is computing derivative here, looking ahead, and that is why it's called forward difference. Okay, forward difference. We can compute derivative at xi plus 1. The actual derivative is this red line. Okay, this red line. Okay, please note that this red line and this red line have different slopes. Okay, however, my function is p2x, so the derivative is this dash slope of the dash curve, and which is we call it backward difference. For p2, Lagrange polynomial second order is both numbers are exactly the same. Okay, now let's look at 3 points. With 3 points, we got with 3 points we have p3 Lagrange polynomial, and is a bit complicated. Here I replace this xi plus 1 minus xi with appropriate hi's. Okay, so you can see that these are the difference between abscissas. Okay, but this function is quadratic. It's quadratic function. Now I will not do the algebra, but you can do the derivatives and compute now at 3 different points. Right? I have 3 different points. So xi minus 1, xi plus 1, and the functions may be like that. I have a picture in the next slide. Just give me a minute. So anyway, these are the functions. Now the real function is going maybe something like this, but I approximate by the quadratic function. Okay, I have only this information. I have nothing more. Now I'm not doing the algebra, but you can compute it at 3 different points: I minus xi minus 1, xi plus 1, and xi. Okay, now trust my word. I mean, I don't want to bore you by doing this algebra, and we get these numbers. So with if I look at the leftmost point, at this point, and compute the derivative, I get minus 3 fi minus 1 plus 4 fi minus fi plus 1. Okay, so coefficients are minus 3, 4, and minus 1 by 2h. But if you look at the derivative at xi plus 1, the rightmost point, then I get a different function. This is a function fi minus 1 minus 4 fi plus 3 fi plus 1. Now these two functions are different. Divide by 2h. Okay, these two functions are different, right? Okay, so the at xi minus 1 is a forward difference because I'm looking ahead, and xi plus 1 derivative computed at xi plus 1 is backward difference. I'm looking backward, and these two formulas are different. See? Now we can also compute derivative at the midpoint. There's a midpoint here, and it happens to be simplest among all three. So fi plus 1 minus fi minus 1 by 2h. Okay, so these are three derivatives, and this, the one computed in the midpoint, is called central difference. Okay, so both are, well, all three are useful formulas, and okay, now let's look at illustration. Now, actually, I should correct. So here, if I use 3 points, then I'll have a point here. Okay, xi minus 1. So this is a plot taken from earlier one. So with 3 points, forward difference will be basically I have another point somewhere here, and this curve is not a straight line; it's some quadratic function. Now the central difference with 3 points is shown here. So basically, compute the slope at the midpoint, and the real slope, of course, is this one. But using the 2 points here and here, and it turns out to be fi plus 1 minus fi minus 1 by 2h. Okay, is something like a straight line going through. In fact, it is equal to this one right now. Though you're using 3 points, but you're just approximating with that. And it is indeed the slope of the quadratic function as well in the midpoint. Okay, with equal distance. Okay, I forgot to tell you that for the derivation in the previous slide, I used an approximation that hi plus 1 and hi are equal. Okay, otherwise the formula becomes very clumsy. Okay, so we assume it to be equal. You can do it for unequal, and many times we need formulas for derivatives with unequal h. Okay, but for teaching, it's best to give a simple formula and explain the subtleties. Okay. Now we can also compute with the 4 points, 5 points, 6 points. You just had to use this Lagrange polynomial, and we can derive all of them. Okay. So when I made the statement that interpolation is mother of many algorithms, it's true. I mean, you can see that I can do derivatives using those formulas. I can compute integration with these formulas, and these are the basis for more complex algorithms like ODE solvers. So it's all connected. Okay. Now this table is a very useful table. You don't need to look at the derivation of how we derive. I mean, you don't need to memorize them, but you should be able to see this table and derive the formulas. Okay, so let's look at forward difference. So forward difference is my points are fi and I, fi plus 1. So I derived that. Remember, I mean, it is fi plus 1 minus fi divided by h. So h has been absorbed here. Okay, h is right here. With 3 points, so now I have 3 points, 1, 2, 3. So there are 3 points. Then I again derive the formula. In fact, is -3 first point, 4 second point, and -1 third point. Divide by 2h. Okay? That's how we read. So just what are the weights for each FIs you get from the table and divide by whatever in the left. Okay. Now backward difference is pretty similar. I have 2 points, Fi and I5 -1. So I look at the derivative at Fi here. So I look at one point to the left of it, or leftward like that, and -1 by h. Okay. Now this table is not exactly arranged like what I derived. I took 3 points, in fact, for derivation here, here, and here. But you see, you can always shift i's. Okay. This is the with 3 points. Backward difference. Central difference, first derivative is here. Fi plus 1 and Fi minus 1 divided by 2h. Correct? Now, if you have 5 points, we can also compute the derivatives. I'm not writing the forward difference and backward difference, but central difference is given here with 5 points. So the middle point, of course, nothing can happen, and no contribution. But 1 and 1 to the end point, there's symmetry for central difference. Well, not symmetry. There's a -1 here. So somewhat the coefficients are equal and opposite to some kind of, okay? And -8 and +8. Anyway, these are the coefficients we see from the table and we compute. Now, all this for first derivative. We can also compute second derivatives. So with 2 points, of course, second derivative is 0. Linear, second derivative is 0. With 3 points, second derivative is not 0. And I didn't derive them, but we can do the derivatives here with 3 points. So x squared will give you 2, right? Every term of the interpolation, this formulas will give, all of them will give you 2, right? And bottom will give us this will give us 2h squared, and this will be -h squared. Okay, and this again is 2h squared. So I should have written the formula. You can see that. So 2 will cancel here. 2 will cancel, but sign will remain the same. So it is Fi plus 1 minus 2Fi plus Fi minus 1 divided by h squared. Okay, so that's the formula. So I hope you can see that Fi plus 1 minus 2Fi plus Fi minus 1. So this is central difference. Second derivative, F double prime at, in fact, with 3 points is same. You can just compute. Well, I mean, this you get exactly the same at any point, right? Because this is x squared, double derivative is always 2. So this is same for any point. I did not write xi, but xi plus 1 and xi minus 1. Okay. Now we can see how to read in this table. Second derivative is here. This is double prime. This is not coming out very well. So this is the double prime formula, and the double formula. All three are exactly the same with 3 points. The midpoint has -2 and the other two have 1, and you divide by h squared. But dimensionally, you know that there's h squared below, right? That's straightforward. Okay. With 5 points, you can also compute the double derivative. Is written here. So you should know how to read this table. Okay, and compute the derivatives.